Thank you, Professor, for your kind introduction. I'm Li Zhang, a PhD student at Beijing University of Post and Telecommunications. Today, I'm going to present our work, LlamaTouch, a faithful and scalable testbed for mobile UI task automation. This work is done with a lot of collaborators from BUPT and Tsinghua University. And let's start with what is mobile UI task automation. Smartphone users often interact with devices through voice commands, and they expect the phone could accurately perform certain UI tasks in place of manual operations. So this process is done by mobile UI agents by operating on each UI until the task is finished. So traditional approaches to automating UI tasks involve writing the fixed rules for specific applications and for specific tasks. And we think they require a lot of programming efforts. And recently, we have seen another trend by using the emerging large language models and multimodal large language models to understand and operate on mobile UI. These models are capable of understanding user instructions and translating their instructions to arbitrary actions on mobile UIs. But this trend raises an unknown question. Can these agents accurately complete user instructions? So it's necessary to evaluate them in the real-world environments. So to evaluate them, the most intuitive evaluation method is through the human validation. And it achieves high accuracy, but with low scalability and high costs. And this is because the human effort is increased with the number of tasks and agents. The second approach is widely used in prior studies. This is mobile agents predict the actions on each mobile UI and compare these actions with the ground truth ones in the static data sets. And it requires the two action sequences are identical. And this is similar to the evaluation approaches in traditional machine learning. But the second approach, we name it the stepwise action match on static data sets, only achieves high scalability because it can run automatically using the programs. But it can't reveal the real capabilities of mobile UI agents, as they can only evaluate certain task completion paths. So therefore, it will lead to high false negative rates because many completed tasks can be done. Many completed tasks can't be identified with this approach. So how to solve this and achieve both scalable evaluation as evaluated on static data sets and faithful evaluation as evaluated by humans? And our key finding is that the UI automation tasks will transfer application states that will be represented on the mobile screen. For example, for the task, open the Microsoft Excel and go to the login page. This can be done through directly open the app and go to the login page if the app is installed. Otherwise, it requires to install it from the Google Play Store and then open it to the login page. So both the two different task execution paths lead to the same application state, the login page of the Microsoft Excel. So based on this finding, our approach is to determine whether a task is completed. We can check application states during and after the task execution, rather than comparing concrete action sequences on static data sets. But the question is, if we can identify what the application states should be, how to annotate them for comparison? And another most straightforward approach is annotate and match at the whole screen level. But this approach can handle the dynamic screen resolutions and dynamic screen contents, like the advertisements. So can we only annotate those essential UI states while ignoring others? For example, in the last screen, we only annotate the text box with the text, sign in and sign up for free to indicate this is the login page. To do so, we need to break down the whole screen into single individual UI components and then annotate only the essential ones. And here is another example for the task, empty the shopping cart on Best Buy. And in this trace, we can only annotate 2 text boxes in the last screen to represent the task is finished. And the first is a URL field, the Best Buy's URL, and we want exact match on it. And the second is the exact match on the UI component with the text, your cart is empty. And all other actions and UI components, we can omit them. So beyond the exact UI component match shown in the example, in LlamaTouch, we also provide a list of annotation primitives to cover a diverse range of information within UI and system states. To summary, there are 2 types of matching design, the exact match and fuzzy match. And the annotation can be done at different levels. For example, the whole screen level, the individual UI component level, the system states, and actions. We also implement the corresponding match logic of these primitives during the evaluation. So with these annotation primitives, we can use prior UI annotation datasets like the Android in the wild as a reference to generate essential state-powered datasets. We also add nearly 400 new tasks to covering diverse daily user applications, and these tasks are annotated from scratch by us. And in our dataset, each task includes the screen representations, including the pixel-level screenshots, the view hierarchies, and Android activities. And there are also the actions on each screen and the task instructions. And what's new in our dataset is the annotated essential states and the task setup process. We use a global Android emulator image with required application installed, and the environment setup scripts for each task. And this ensures the nearly identical environment before the task is evaluated. Another design of LlamaTouch is the UI automation tasks must be evaluated in real-world environments rather than predicting actions on static datasets. So we build Agent In. It includes a list of APIs to bridge the mobile UI agents and the real-world mobile environments. The task evaluation is conducted offline. It uses the traces saved by the Agent In. And with the saved traces, the LlamaTouch evaluator will compare this trace with the predefined essential states in LlamaTouch dataset for comparison. And let's put them all together to see the overall workflow of LlamaTouch. And we have tried our best to make it easy to use. The users only need to integrate their mobile UI agents to Agent In, and then implement the trace evaluation logic with only a few lines of code. And the next is our evaluation. We want to answer the key question: can LlamaTouch evaluate mobile UI agents with high faithfulness? For this purpose, our metric is the accuracy of different evaluation methods. And we take the human validation results as a ground truth. If an evaluation method generates the same result as a human validation, it is considered a correct point. And we select 2 baselines, and they are all action match-based evaluation methods on static datasets. The first one is the step-wise action match, and it requires 2 action sequences are identical. And the second is some improvement over the first one. It can tolerate some non-essential actions between the ground truth actions. And for the used mobile UI agents, we selected the AutoDroid, AutoUI, Coco agent, and App agent. They are all powered by multimodal large language models and customized models. So finally is our result. And the left table shows the result of the end-to-end task completion rate and the accuracy of different evaluation approaches. And our first finding is the action match methods failed to evaluate tasks, and it only shows an almost 0 task completion rate. LlamaTouch reports the task completion rate closer to human validation. And another interesting is all the methods show high accuracy, and there are most false cases. And this is because the UI agents can't complete most requirements in real-world environments. So we then evaluate how does LlamaTouch perform in completed tasks, and we want to show whether they can reduce the false negative cases. And the result shows us significant differences. And among all the successful tasks validated by human annotators, the LlamaTouch achieves nearly 80% accuracy. But the action match approaches achieve nearly 0 accuracy. So LlamaTouch significantly reduces the false negative cases. To conclude, LlamaTouch is the first faithful and scalable testbed for mobile UI task automation. LlamaTouch is also highly extensible. It can integrate new UI automation datasets, new annotation primitives, new agents, and even new real-world mobile environments like real-world smartphones. And finally, the LlamaTouch is fully open-sourced. We have open-sourced the annotation platforms, the dataset, the evaluator, and the mobile UI agents we used in our paper. And if you are interested, you can scan this QR code or access this URL to check our project. And thank you for listening. I'm happy to take questions.
Mingyuan Zhong from the University of Washington. Really cool work. I think this addresses a really important gap in evaluating mobile agents. One question I have is, how do you see this system address like side effects that might happen while an agent is operating a device? So let's say I asked a model to order me some coffee, but it adds maybe like a sandwich, or orders a sandwich first and then orders a coffee. So eventually, at the final stage, you still get the coffee, right? But in the middle, there's a side effect. Can you detect that, or do you plan to detect it?
Thank you for the question. And actually, in LlamaTouch, you can also not only define the final state, but you can also define the middle state. So if you think the sandwich ordering is your middle state, you can just define some primitives like the states after you successfully order the sandwich.
Oh, I mean, like if I don't want a sandwich, right? But it just goes on its own and orders something that I don't want. Do you think it will be able to detect that side effect? I mean,
I think that might be an appropriate test case in LlamaTouch. Right. And actually, in LlamaTouch, for the nearly 500 tasks, we carefully selected them to make them can be represented using the essential states that we developed. So,
okay.
Yeah.
Yeah, that's cool. Thank you.
Thank you.
All right, so maybe the next speaker should start setting up. We've got one question while they are. So there's this nice kind of back and forth between the systems that we build and the evaluations that we create. And I was wondering if you have any thoughts on how this evaluation might actually impact how people go about building agents, or what does it take to do better on your evaluations? Is there some insight there that you can help us with?
Thank you. Our initial incentive to build this work is to evaluate whether the agents can be used in real-world environments, because there is a trend that these mobile agents are initially built from the AI industry, so they often trade on a lot of mobile UI screenshots and then only predict a single action on this UIs. But we think this is not the case when the actions actually operate on mobile UI environments. They actually operate on the real-world environments. So in our evaluation results, you can see that nearly most of the mobile UI agents, they can't finish these tasks in real-world environments. And we hope these results could provide some insights for the agent developers to focus on how to make them practical in real-world environments, like remember a lot of things from the history, how the users operate on their phone, or build more data sets to train these models on a lot of mobile UI pairs to let them learn from their UI representations.
Awesome. Well, thank you again.
Thank you.